Hello everybody, I'm Professor Herzog. Today we are going to talk about ordinary differential equations, and we will study in particular the ordinary differential equation of the Solow-Crouse model. The Solow-Crouse model has the following form. The capital labor ratio, the change of the capital labor ratio, equals the saving function S times A times K of t alpha minus the depreciation function. This differential equation is the key element of the Solow-Crouse theory. And what I'm going to do next is I show you how to solve this differential equation. In order to solve this differential equation, we follow three steps. The first step is we have to transform this differential equation into a new one, which is a little bit easier to solve. So in order to transform, I assume a new function. I say, let's assume there is a function u of t that is the same as k of t 1 to the power of 1 minus alpha. And I also calculate the derivative of this new function because I have the derivative in my initial function. So the derivative of this function is u dot of t is equal to 1 minus alpha k of t minus alpha times k of t dot. We need these two functions because now in our first step I substitute for k dot of t in my first equation, and for u of t later on I will substitute it in here for my k of t. So for this we simply rewrite this equation as follows. On the left hand side we have k dot of t, but k dot of t is, according to this equation, the following part. It's u dot of t over 1 minus alpha kt minus alpha. And on the right hand side of my equation I still have the saving function, which is s times a k of t alpha minus n plus delta k of t. Yeah. So what I have done here, I have simply substituted for k dot of t here on the left hand side my new function. And in the next step I factor out here on the right hand side k to the alpha. So I factor out k to the power of alpha, and I rewrite then what is in the bracket. It is just s of a minus n plus delta k, and then we have here 1 minus alpha. And this is very interesting because k to the power of 1 minus alpha, that is my u I have defined before. So I can substitute in here the u in a moment. And what I have here in the denominator on the left hand side, that can be now multiplied through this equation, and then you will see this k to the power of 1 minus alpha cancels with this k. So what I obtain is simply the function of u dot of t is equal to 1 minus alpha, this k and this k cancels, and then I have in the bracket s times a minus n delta u of t. Okay, that is the first step, because now we have the same differential equation, just with the variable u. And in the second step I have to solve this differential equation. And in order to solve this differential equation, I use a theorem. And the theorem basically says we can find the general solution of this differential equation in terms of u first by solving the homogeneous part plus adding the inhomogeneous part, just one particular solution. So let's do this. So in step 2, I have to solve first, as I said, the homogeneous differential equation. The homogeneous differential equation looks, given my u equation, as follows. It is if we go back for a moment, it is u of t 1 minus alpha n times SA, that is 0 for the homogeneous part. So it's just u of t 1 minus alpha in the second part. So it is 1 minus alpha n plus delta, then there's here a minus in front, u of t. So this is the homogeneous differential equation, what we label homogeneous. And this differential equation is what we have solved in another class already. This is a simple ordinary differential equation like the population Crouse model. And we know already the solution for this one. So this has the solution u of t is the integration constant c times e to the power of minus 1 minus alpha n plus delta times t. This is the first part of the solution. It's the solution of the homogeneous differential equation. And to have the general solution, now I have to find also the inhomogeneous solution. And that is what we'll do next. So the inhomogeneous differential equation, is basically the same equation we have derived a moment ago, u dot of t, but we simply factor out 1 minus alpha, and we factor out the constant term n plus del. And then we have here in the bracket s times a over n plus delta is minus u of t. So this is the inhomogeneous differential equation of our problem, just by rewriting it and factoring out this term, n plus rho, out of the bracket. And the theorem says, in order to solve this equation, we just have to look to one point. And the point we are studying is our steady state. It's the point where u of t is equal to 0. This is our steady state point. So I plug in here on the left-hand side 0. So now we have to see, when is the right-hand side 0? Well, if on the left-hand side we have 0, you see immediately the right-hand side is 0 if this bracket is 0. And the bracket is 0 if we assume that u of t is s times a n plus delta. And this is now the solution of the inhomogeneous part. So in order to have the general solution, I just have to add up both the inhomogeneous solution and the homogeneous solution. And that gives us then the final solution. So let's write down the final solution. So the general solution of this problem, u of t, is the inhomogeneous solution, which is 1 minus alpha n plus rho t, plus what we have derived, the inhomogeneous solution, which is this s times a over n plus rho. So what we have here is now the general solution, and it consists of the homogeneous solution plus the inhomogeneous solution for one particular point in our steady state. And so we are almost done. There is just one final step we have to do, and this is we have to retransform the equation from u to k, because the first equation was in respect of the capital labor ratio, k. So remember that u was defined as k to the power of 1 minus alpha. Well, I can reverse this. This implies that k of t is nothing else as u to the power of 1 over 1 minus alpha. So I just bring the exponent to the other side, and now I have the function in respect of k. So now you see immediately the general solution in respect of k is the solution of u, which we have here. Just in the exponent we have to write here 1 over 1 minus alpha. And that gives me the solution in respect of k. So I will do this to finalize this discussion. So now let me write down the final solution in respect of k. So the solution in general of my capital labor ratio in the Solow model is the following function. So it is my c e minus 1 minus alpha n plus rho of t plus the inhomogeneous part was s times a over n plus rho. And now we have here the exponent, as I told you, just to the power of 1 over 1 minus alpha. This solution is the solution of the ordinary differential equation in the Solow-Crouse model. The only thing we can, of course, discuss in a further discussion is the integration constant. The integration constant, as you know, is probably determined by the initial condition. And the typical initial condition in the Solow model is the assumption what happens if the capital labor ratio is at the beginning, at time t 0. And you see immediately what happens. Well, if I plug in here in my general solution t equals 0, then we see immediately there is this t here. So if I have t0, then the whole exponent of the exponential function is 0. That means the exponential to the power of 0 is 1. So what remains is this term. So there's just the integration constant. And this, of course, is independent of 0. So that also remains s of a divided by n plus rho. And of course we have to care about the exponent. And now you see from this condition we can simply rearrange by algebra in respect of c, and when we have the integration constant then we can plug in this term in this position. And then we would have the complete general solution of the Solow-Crouse model. I hope you have seen how to solve the general Crouse theory and the general solution. Have a good day. Bye bye.